Hello students, now today we will discuss DC biasing of BJT in analog electronic circuit. So already I told you what is DC biasing and different types of biasing, like is your fixed biasing, collector to base bias or feedback bias, emitter bias and voltage divider bias. So in all the four biasing methods we have discussed, and we have calculated, and performance of each biasing can be analyzed through stability factor. And stability factor is nothing but what? The change in like your leakage current or VB and current application beta with respect to IC. How far your operating point means ICQ and VCQ is stable with respect to transistor parameters. If the transistor parameters will vary by means of when the transistor will operate, that is your temperature increases. If the temperature increases, leakage current increases. So how will you stabilize the leakage current? By means of stability factor expression, we will analyze whether particular biasing is stable or not. In case of out of four biasing methods, voltage divider biasing is the most suitable biasing method among these four biasing methods, like is your fixed bias, self bias or collector to base bias and voltage divider bias. Out of these four biasing methods, we have preferred the what? Voltage divider biasing. Voltage divider biasing. Why we will choose voltage divider biasing rather than other three methods? Because of stability point of view. Transistor as an amplifier means what? Amplifier means to raise the strength of the weak signal. Once we get the amplified output, that means without disturbance, whatever the input, exact same without change in shape, and we just magnifying its amplitude level. We can say that the transistor, the input is amplified by means of amplification factor. So in case of voltage divider biasing, the operating point or Q point is nothing but the zero signal values of IC and VC is more stable compared to your fixed bias and collector to base bias or feedback bias. We have discussed all the things related to transistor biasing. Now today we will do the numericals or problems related to transistor biasing. In a DC biasing of BJT, particularly in these problems or in these numericals, the question asked, find out the IBQ. Q means what? About the Q point or operating point. We have to find out the DC current on DC voltage. The IB is nothing but base current. IC is nothing but your collector current. VC is nothing but your collector voltage potential at, and this is your base, and this is your emitter, and this is your collector. So first find out the DC voltage VC, V and VB. We have to find out, and this in these examples, as far as the DC biasing is concerned, this is a capacitor, input capacitor, and this is your output capacitors. As far as DC is concerned, we should remove this capacitor because of infinite reactance. Reactance will be more, that's why it can be open circuited. When we will find out the DC current and DC voltages, so you have to simply replace the capacitor value. So capacitor can be open circuited here. So if we will say VC means what? This is your collector potential, and we can say this is nothing but is a VC. That means this with respect to ground is your VC, because this is your collector terminal, and potential at this point with respect to ground is nothing but is your VC. Similarly, I can say this is your emitter terminal. This is nothing but your what? VE. The potential at this point with respect to ground is nothing but V or emitter potential. Similarly, also we can say that this is your VB. This base with respect to ground, this is nothing but your VB. We have to calculate, or we have to find out the value of DC current, like base current, collector voltage, and emitter voltage, and VB, and also and VCE, collector emitter voltage. So how will you calculate this one, the DC current and DC voltages? As far as to calculate the DC current and DC voltages by means of proper application of KVL, Kirchhoff's voltage law. Kirchhoff's voltage law means you have to apply Kirchhoff's voltage law to the input and Kirchhoff's voltage law to the output. Solution. So here what you will do? So in clearly this figure is nothing but your voltage divider biasing configuration. In voltage divider biasing configuration, there are two approaches. One is your approximate analysis, another one is your what? Exact analysis. In approximate analysis, what is the condition? Already I told you in the previous class, beta RE must be greater than equal to 10 times R2 here. So if you will choose approximate analysis, in approximate analysis, what is the condition? In approximate analysis, that is your condition is what? Beta RE must be greater than equal to 10 times R2. If this condition is satisfied, we will follow the approximate analysis. What is approximate analysis? Already I told you in the previous class. So here beta RE, here beta value is how much? This is 100, and this is your RE value is how much? That is 1. That is nothing but what? Which is equal to 100 kilo ohm. Is it greater than equal to 10 times R2? That is your 10 into 2.2. 10 into that is your 2.2 kilo ohm. It is nothing but what? 22 kilo ohm. Obviously, this condition is satisfied. So 10 beta RE greater than equal to 10 times R2. That's why we can follow approximate analysis. In approximate analysis, satisfied. So that is your beta RE greater than equal to 10 times R2. This condition is what? Satisfied. If this condition is satisfied, then what we will do? That is you can calculate the voltage across. This is nothing but let R1, and this is nothing but let R2. In the voltage divider biasing, the voltage, the total voltage, this is your VCC, is divided between these two resistance R1 and R2. Voltage across R1 is V1 and voltage across R2 is your V2. So V1 plus V2 is nothing but your VCC. So what? We have to calculate it first. This is nothing but your what? Now V2. So VCC equal to V1 plus V2. In approximate analysis, VCC, the total voltage is nothing but your V1 plus V2. And V2 value is how much here? V2 is nothing but what? Is the total voltage your VCC. The voltage across R1 plus voltage across R2 is nothing but VCC. And this voltage is nothing but, you can apply the voltage division rule, VCC into R2 by R1 plus R2, or you may calculate the current. Current is nothing but total voltage VCC by R1 plus R2. I equal to VCC by R1 plus R2. So I can write V2 is nothing but I into R2. In approximate analysis, this current equal to this current plus this current. This is I1, this is your I2, this is your IB, base current. Since this terminal is connected to the base, and this is nothing but current flow is nothing but base current. And this is nothing but I1, and this is nothing but your what? I2. So in approximate analysis, we have neglected the base current. So that's why if base current is neglected, this current is nearly equal to 0. So I1 equal to I2. If I1 equal to I2, I1 is nearly equal to what? That is your I2. If the current same, the resistance R1 and R2, if the current same, since it is nothing but what? The currents are the resistance are in series. Now the resistance are in series. The total current value is how much? The I equal to how much? I equal to I1 equal to I2 equal to, that is your total voltage, your VCC, divided by R1 plus R2. Okay. So this is nothing but your VCC. So VCC divided by R1 plus R2 is your current. So that is your I. And V2 is nothing but I into R2. That is your I value is how much? VCC by R1 plus R2 whole into what? That is your R2. The value is how much here? VCC value is your, suppose let VCC equal to 20 volt is given. VCC is your 20 volt is given. So that is your 20 divided by R1 plus R2. R1 is your 55, R2 is your 10. 55 plus 10, that is your what? 65 into R2. R2 is your 10. And the value will be how much? That is your 200 divided by 65. 200 by 65, and that is your what? That is your 200 divided by 65. The value is your what? That is your 3.076 volt. So V2 value is how much? This one. Then apply Kirchhoff's voltage law to the base emitter loop. We have to apply Kirchhoff's voltage law to the base emitter loop, this loop. If you apply KVL to the base emitter loop, what is my equation? This is your V2, minus 2 plus plus V2, and there is a potential between base and emitter. We can say what? That is your VBE. So V2 minus VBE minus current in resistance. What is the current? This emitter terminal, obviously the emitter current will flow. That's why I into RE equal to 0. If you apply KVL, apply Kirchhoff's voltage law, apply KVL to the base emitter loop. What is my equation? If I apply KVL to the base emitter loop, what is my equation? Minus to plus plus, that is your V2 minus, if there is a base and emitter, there is a potential. You have to consider here the VBE, it is 0.3 volt for germanium and 0.7 volt for silicon. If the question does not mention the VB value, you take as VB equal to 0.7 volt as like your silicon transistor. Normally, we are using the silicon transistor, that is your VB equal to 0.7 volt. So here V2 plus minus VBE, then here plus minus current flowing like this. This is your plus and this is your minus. VB minus IERE equal to 0. This is my equation. So V2 value already we have find out the VC value, V2 value is how much? 3.07 volt. VB value is 0.7. RE is given. You can easily calculate the emitter current IE. So that's why V2 minus VB, IERE equal to how much? From this expression, what? That is your IERE equal to V2 minus VBE, or IE equal to V2 minus VBE divided by what? RE, which equal to V2 value is how much? 3.07 volt. 3.07 minus VB is your 0.7. RE value is your 1. And the value is how much here? So 3.07 minus, that is your 0.7. The value is how much? 2.37 by 1 is same value. That is your 2. This is nothing but 2.376. That is your 1. Remember, this is 1 kilo ohm. 1 kilo means reciprocal of kilo, that is your milliampere. So you have to write down emitter current IE equal to this is milliampere. Why I am writing milli? Because 1 kilo ohm. Remember the denominator is your 10 to the power 3. If the denominator is your 10 to the power 3, then it can be write 1 by 10 to the power 3 is nothing but 10 to the power minus 3. So 10 to the power minus 3 is nothing but what? Milliampere. So that's why emitter current IE equal to your, that is your 2.376 milliampere. Then here beta value is given. If you want to calculate the IB is nothing but what? IE emitter current IE equal to, that is your IC plus IB, or you know the emitter current, the IC equal to beta IB. Remember the beta is your 100 is given. So IC by IB equal to beta. So that's why you can write down here IE equal to what? I equal to here IC equal to beta IB, here also IB, and this is nothing but what? If IB taking common, that is your 1 plus beta whole into IB. So IE is nothing but what? 1 plus beta times base current. And IE you know, IE equal to how much? 2.376 milliampere. IE equal to 2.376 milliampere. Beta value is given 100. You can find out what? IB. So that is your IB. From this expression, IB you can easily calculate IB. So IB equal to, so IB is nothing but IE divided by 1 plus beta, or IE equal to given, that is a 2.376 milliampere divided by 1 plus beta. 1 plus 100 is nothing but what? 101, and the value is how much here? That is your 2.376 divided by 101. the value is nothing but 0.023, and this is nothing but 0.023 milliampere, 0.023 milliampere, or this is nothing but 0 IB. IB is nothing but same IBQ, or IB about the Q point, same IB you can written as IBQ equal to how much? I can write 0.023 milliampere if you convert it to microampere, because the base current must be converted into microampere. Micro is nothing but 10 to the power minus 6. Here 10 to the power minus 3. If you again put the decimal point here, that is a 23 microampere. So IBQ equal to, that is a 23 microampere. So this is nothing but your what? IB. And you can find out, already you got IB. Then you can easily find out IC. IC equal to what? IC equal to beta IB. IC equal to beta IB. IC equal to beta IB. Beta is your 100. IB is your, here you can write down 0.023, and it is around what? That is your 100 means after 2 digits it becomes what? 2.3. IC is nothing but 2.3 milliampere. This is nothing but what? That is your IC. IC is nothing but what? ICQ. Okay. Then we have to find out, that is your what? VC, V, VB and VC. Okay. So then what we'll do? How to calculate VC? Okay. So we have to calculate, that is your VC. VC is how much? VC means collector potential. So collector potential VC means what? This with respect to ground. Total voltage your VCC. So VC means this with respect to ground VC. VC equal to total voltage VCC minus this drop. And this drop is how much? IC into RC, because this is a collector terminal. Obviously the current flow through this RC is nothing but IC. So I can write here VC is nothing but VCC minus ICRC. Is not it? Because the total voltage, this with respect to ground is your VCC, and I want to calculate this. VC means potential at this point with respect to ground. Total minus this drop is nothing but this. So that's why VCC minus this drop. This drop means current in resistance. Current is nothing but IC. That's why IC into RC. So IC into RC. Already you got IC value. IC value is nothing but what? IC value is your 2.3 milliampere. So here VCC equal to how much? VCC is your 20 volt given. That is your IC. IC is nothing but 2.3. RC into RC. RC value is your 2.2 is given. RC value is your how much? 2.2. RC is your 2.2. And the result will be how much? That is your 20 minus. That is your 2.3 into 2.2. The value is how much? 5.06. That is your 5.06. So that is your 20 minus 5.06. The value is your how much? 14.94. That is your 14.94 volt. So that is your VC equal to 14.94 volt. That is your collector potential with respect to ground VC. Okay. Then find out VE. This is your VE. V means the emitter potential at emitter terminal with respect to ground. Obviously, there is only resistance here. RE means 1 kilo ohm. So if I will multiply current, emitter current with resistance RE, this is nothing but V. V is simply what? I into RE. So VE equal to, that is your IE RE. So IE value is your how much? IE here 2.376. 2.376 into RE value is how much? 1. So this is nothing but, this is, remember, this is milliampere and this is kilo ohm. Milli means 10 to the power minus 3. Kilo means 10 to the power plus 3. So 10 to the power minus 3 into 10 to the power plus 3, that is your 10 to the power 0. 10 to the power minus 3 plus 3 is your 10 to the power 0, that is 1. So milli and kilo, that will be cancelled out. Only that value is how much? 2.376 volt. This is nothing but your VE. This is nothing but your VE. Then another one is your what? That is your VCE. VCE is how much? VCE. So already I told you in your previous class. So VCE is nothing but potential, the potential VC minus VE. So how VC minus VE? Already I told you. So applying KVL to the output loop, and whatever the expression, that is your VC. VC means what? VCC minus ICRC. V means IRE. So VCC minus ICRC minus IRE equal to VCE. So that's why VCC minus ICRC, in place of VCC minus ICRC, this is nothing but VC, and IRE is nothing but VE. So that's why VC equal to VC minus VE. So already I told you in your previous class. So VC value is already you got. VC value is how much? 14.94. So that is nothing but 14.94. V value is your what? 2.376. The value is how much here? So 14.94 minus, that is your 2.376. 2.376. The value is how much? 12.564. 12.564. This is nothing but your VCE. Okay. So VCE, we got VCE. VCE equal to, that is your 12.564 volt. Okay. Then another is what? That is your VBE. VB already 0.7, you know. So that is your VB. So VB is nothing but what? VB we know that VBE equal to VB minus VE. VB minus VB. V. So if you apply KVL to the input loop, you will get the input equation, that is your V2 minus VB minus IR equal to 0, or we can say that this is nothing but VB, means base with respect to ground. In V2 is nothing but your VB. V2 is nothing but your VB, because the potential at this with respect to ground. We can say V2 is nothing but I2R2, VB also I2R2. So, or you may put here VB. VB is nothing but VB plus VE. So VB is nothing but minus VE come to the LHS becomes plus. That is your VBE plus VE. We got VE value is how much here? VE value is your VE is your what? 2.376. So that is your 2.376 plus V plus VB is your 0.7. The value is how much here? So that is your 2.376 plus 0.7. The value is nothing but 3.076. 3.076 volt. Already this is nothing but V2. We have already calculated. V2 is nothing but VCC into R2 by R1 plus R2. Exactly match. That is your VB equal to 3.076. So here, whatever the DC current and DC voltage, first of all we have calculated IB. IB is nothing but your base current. Base current is nothing but here 0.023 milliampere or 23 microampere here. And then we calculate IC. After getting IB, IC equal to beta IB. IC is your 2.3 milliampere here. Then IC is nothing but same ICQ about the Q point. ICQ means about the Q point. So IC is nothing but 2.3 milliampere. Then that is your emitter current IE. IE is nothing but what? 2.376 milliampere. Then calculate VC. VC value is your what? VC equal to 14.94 volt. Then VE. VE is your 2.376 volt. Then VCE. VC is your what? VC is your 12.564 volt. Then we have calculated VB. VB value is nothing but 3.076 volt. So here the Q point or about the operating point, if the question mentioned find the Q point. So indirectly the question asked, that is your what? That is your to find the collector current and collector emitter voltage. ICQ and VCQ. ICQ is nothing but IC 2.3 milliampere. VC is nothing but 12.564 volt. So about the Q point means what? So if in IC like this, that is your, this is nothing but your Q point, and Q point, this value, this is nothing, this axis is nothing but collector current axis, IC axis, and this X axis is nothing but your VCE. So that's why the Q point should be lie middle of the load line, because to stabilize the Q point should be always lie the middle of the load line. The Q point should not be disturbed, and it should not be shifted toward the saturation region, because this is your saturation region. In saturation region, current will be maximum and the voltage will be minimum. This is your current axis. So VC, that means your Q point means here the middle of the load line, that is your what? The Q point should not be disturbed. To stabilize the Q point, we are going to choose a proper biasing method. So in proper biasing method means what? In case of DC biasing for BJT is concerned, we have to prefer what? The voltage divider biasing, because voltage divider biasing, we have stabilized the Q point. That means whatever the variation of the transistor parameters, the Q point is independent of the variation of the transistor parameters. So that's why we are preferring the voltage divider biasing rather than other biasing methods like your fixed bias, collector based bias, and your emitter bias. So that's why in this type of problems, this is the basic how to solve the numericals as far as biasing is concerned. Simply you have to apply Kirchhoff's voltage law to the input and Kirchhoff's voltage law to the output. If you properly applied KVL to the input and output, you will get two equations. Whatever the unknown quantity is given, you can easily calculate it. So next class we will do more and more number of problems related to that is your DC biasing of BJT. Thank you.